Thank you for the nice talk, Huaicheng. Now let's take some questions from the audience. I believe Jongyu is here. He also had a question on Slack. Can you please unmute yourself?
Oh yeah, hello. Can you hear me?
Yep.
Yeah.
I have several questions. First, I'm curious about the overall throughput of the storage array, since it seems like every I/O request requires additional XOR calculation, and it can be a bottleneck in high-performance storage systems. Also, can the concept of IODA benefits non-RAID storage too?
That's a good question. By the way, can you hear me? Okay.
Yeah.
So regarding throughput, so actually it is IODA's, highest goal to not sacrifice the throughput, as prior work. The reason that, IODA doesn't, sacrifice the throughput too much is because that, it doesn't enforce reconstruction for each IO. Specifically, the fast fail, signal represents, all the, give us an accurate signal on the slow IOs that we want to reconstruct. So it only represents a very small percentage of IOs that experience GC. So ultimately from our workloads, only 2 to 10% of IOs that we will reconstruct. And for the second part of the question, so whether IODA can be used for non-RAID scenarios, so the short answer is probably no. So we need to rely on some kind of data redundancy for it to work. But considering that data redundancy is commonplace for existing storage systems, so I don't see that is a major hurdle to adopt this approach in broad settings.
Thank you.
Thank you.
Right. Thank you for the question. Now we have another question from Jeff Koenig from Harvey Mudd College. So the question is, there have been other efforts along these lines. For example, oh, sorry, Jeff is here. I can allow. Can you please unmute yourself and ask the question? We can't hear you. You're muted.
Thank you. If I can figure out how to run Zoom, then I can do it. So there have been other efforts along this sort of lines. I remember one where I/O was issued to every drive in a RAID, including the parity drive. And then if one drive was slow, the I/O would be aborted and they would reconstruct the data. How does your work compare to those systems?
That's a good question. Yeah, we do have one prior work that works on a similar idea to use reconstruction for performance. But specifically for IODA, we focus on how to enhance the PRM interface, to do it in a gray box manner instead of doing it in a white box manner. So as IODA contributions mainly consist of the interface level changes, the host side, management, software management, for the PRM interface, and how to formulate the time window length, so that vendors can set a proper time window without breaking the predictability contract. You are still muted.
Thank you.
Thank you for the question.
All right. Thank you for the question. I have a question as well. So I'm curious, how exactly do you do the synchronization between all these different flash devices to ensure that enough of them are in this predictable latency window?
Oh, that's a great question. So specifically, during the configuration phase, so each device will advertise, the supported time window range. And the host side, will decide, what time window it will use, for all the devices. With that set, all the devices will know that, at what time it will perform under, what kind of, performance mode. Specifically for SSD0, and if you're considering a 4-device array, then SSD0 will always be in, busy mode at, time window 0, time window 5, etc. Go on. And this is something that is relatively simple, for the SSD controller to keep track of. so that the SSD itself can do this predictable and unpredictable transition by itself without coordinating with other device a lot.
Okay, thank you. I'm monitoring the Slack here. There is a question from Brian. So I don't see Brian here, so I'll read the question. So Brian Kim from Syracuse University is asking, well, first, thank you for the excellent talk. Do you assume that the SSDs have the same performance characteristics? If the SSDs exhibit different performance curves due to heterogeneity, how would this complicate your design?
Oh, that's a great question. So currently, our IODA prototype only considers an array, consisting of, same device models. So we haven't really thought about, how it can be, applied to, arrays consisting of different, SSD models. But I do see that IODA can be applied in that scenario as well. So essentially, we, read performance is universally fast, across different SSD models. So that is not a problem. So the tail latency mainly comes from, the cases when the background processes, is happening. And for those cases, so I think, we can extend the existing IODA prototype, to handle different SSD models so that, we can use a universal time window length that can be applied to different SSD models safely.
Right, thank you. There's one more question. Can you please unmute yourself, Shudong?
Oh, yes, no problem. So I mentioned, so I noticed that in the talk you mentioned that the device can autonomously transit into busy state. And so it is possible that even with time window coordination, there could be more than one busy SSDs at some point, so that you cannot really like reconstruct the results. Is that possible?
Without a IODA design, it is possible. That's actually the case that IODA tries to eliminate. We try to formulate a case where at most one we have at most one busy device in the array for the RAID 5 scenario. In that sense, all the reconstruction process will be fast.
So because you mentioned that the device can autonomously transit into busy, right? So yep. Like I was actually thinking that so even with your coordination, you have already scheduled it. So is it possible that one device which like in your schedule should not be in busy state suddenly transit into busy? So
autonomous transition, from predictable window to unpredictable ones is one major drawback, of the PRM interface that we try to overcome here. So as in the design, we do not need the SS with the proper setting of the time window length. So the device won't need to, to do that such, autonomous transition by itself. So without, those autonomous transitions, so basically the host side can ultimately determine, it can have, the predictable latency by reconstruction or when the IO is not busy at
all. Okay, thank you.
Mm-hmm.
Thank you. So this is our time for the Q&A for this paper, but we can take more questions at the end for the panel discussion. So I see that there are more questions in the Slack channel. So thank you again, Huaicheng, for a very nice talk and for answering the questions. We'll move on to the third paper in this session.
Hello there.
Okay, so I cannot see any question on the Slack, and please bring up Huaicheng.
I'm here.
Huaicheng is here. So okay, so any questions from
there is a hand raised.
Yes, but I cannot find him. Okay, so let's start from my part of questions. Okay, so just for clarification, so you need to change the hardware. For example, you replace the FTL?
We need slight change in the firmware side, but we do not, change the major policies that's used in existing FTL designs. Mm-hmm. So That's actually one major design goal of IODA, to only touch slightly on the device side, but leave, the management complexity to the host side.
So the other part will be in the kernel of the operating system, right?
Yep, that's true.
Okay, so that part will do something like the software read, right?
Yes,
Okay.
yes.
Okay, so how can I, okay, Huaicheng, go on.
Hello, can you hear me?
Yeah.
Yeah.
This is Huaicheng from USTC in China. Thanks for your wonderful talk. I have a short question. I'm curious about the overhead of NVMe PLM. Could you talk about it? I think it may reduce NVMe I/O performance, I guess. Could you talk about it?
Yeah, sure. NVMe predictable latency mode is a recent, standardized interface, to help host SSD code design in order to improve performance. Actually, as I can see, so it exposes very small overhead because the interface functionality is relatively simple. It only allows the host, to query the device status on whether it is being busy or, being idle. And the second interface is basically, from the host side to control which state that the device should be in. So it's a very lightweight approach, which, IODA prototype built on top of too, but, we aim to further enhance this interface, to be, to help us achieve more predictable latencies, without heavy re-architecting the device side.
Yeah, I see, I understand. Thank you.
Thank you for the question.
Okay, so do it mean that PLM is, from my understanding, PLM is a specification, right? So you need to implement a PLM, right?
Yep. Yeah,
so
that's true.
Okay, so you put your capability inside the SSC devices. Okay.
It's not like putting the capacity into the device, but rather this work, focuses on how we can, manage PLM from the host side, how to enhance it, at the interface level, and how to, which can further enhance us, give us the opportunity to achieve always predictable latencies. So I would say that, the contribution of this work is mainly focusing on, the interface level changes, to improve PLM and the software mechanisms to manage PLM.
So you needed to maybe from the kernel level, you tell the, for example, you tell the SSC devices that it is a time for the device to put the device in busy time mode, right?
Yeah, that's the innovation of the time window synchronization part. So because we need it because, in order to get always predictable latency, so we can only allow at most, one busy SSD at any time for RAID 5 setup. So for those cases, so we need, to coordinate when each SSD will be able to perform GC safely without, breaking the predictability contract overall.
Okay, so this is coordinated inside the kernel, right?
Well, yeah, you can say that, but it's just, some as simple as, sending down some, simple command to the device, to instruct the SSD to enter, certain states.
Okay, so we have one question from Yun Fan from National University of Singapore. So how difficult is it to modify the SSD firmware? Is it possible across different hardware vendors?
That's a great question. Yeah, as I mentioned earlier, so we only slightly touch, the firmware side, but rather, didn't touch the major logics in, for example, the GC policy, in which is, has been developed by SSD vendors for many years. So that's not something that we target to change, in this work. Rather, our firmware changes only involve, the interface level changes, and for example, to pass our fast fail signal, which is passed down from the host side, and to decide when it is safe for the device, to perform GC. It's just like, delaying the GC operation for a certain amount of time and in order to synchronize all the GC behaviors across all the devices in the array. We believe that these kind of changes are relatively small and very lightweight, without changing any of the existing firmware logic at all. So we hope that this kind of slight changes will help us, will help the deployment of IODA in the future.
Okay, so you do need some special, maybe something like open channel SSD, right? So some closed channel SSD, you cannot change the firmware. You need some some functions to the up layer software, and then you can implement IODA kind of functionality, right?
The idea is not dependent on open channel SSD, but rather the major focus is actually for today's commercial SSDs, which are black box.
But you cannot
the platform that we use. Yeah, the platform that we use is an SSD emulator, which we have access or full control to the firmware side. We also have a prototype implementation on an open channel SSD, but for that specific case, we mainly use open channel SSD, as a black box SSD, which we can modify the firmware. So that's just, our idea to validate the idea, on a real platform.
Okay, I see. So, can you give maybe us some other unit scenarios other than SSD array, because you only discussed the applications for SSD arrays?
Yeah, sure. So basically, the several principles that is proposed in this work is, widely applicable, to other applications domains as well. For example, the fast fail interface, basically advocates, a hardware interface design where, tell the application, tell the user, whether you're busy or not. So this is not, it can be, as I can see, used for other type of IO devices, such as, NIC cards, when it is under, heavy head of a line blocking. And it is not, just limited, to work with, background activities such as GC in NAND flash, but rather any kind of background operations, which could, introduce unpredictability to the host side. For example, when you experience, high queue depths, and this can potentially introduce another, tail latency source. So we believe the interface change can work with, those scenarios as well. On the other hand, so the time synchronization mechanism is also not uniform, not only works for flash arrays, but rather for different distributed storage systems where we have abandoned redundant data that we can potentially proactively use to reach the data in a much lightweight manner to reduce latency.
Okay, so since there are no more questions, maybe thank you again, and let's turn to the last paper.
Thank you.